Hello, this is Ryan Butler, and welcome to my AST 613 Fundamentals of Astrophysics 1 Final Oral Examination. In this exam, I will be covering two questions, the first of which deals with stellar timescales, and the second of which deals with ionization states. To begin, I'll look at the three stellar timescales, the freefall, Kelvin-Helmholtz, and Einstein times. I'll derive each of them, and look at a solar mass for each time. We'll then focus on the Einstein timescale briefly for the Sun and an O-type star and see why they're different. Following that, we'll pivot to our ionization states. We'll look at how they depend on temperature, what that means for the population levels in the hydrogen atom, and what it implies for the spectrum of A-type stars. To begin, we'll consider the freefall timescale. In this timescale, we're considering a cloud of gas in space that's been shocked or something to collapse. Its collapse will not be fettered by any process, so it's basically just collapsing down to a point and we're getting the time for it. Our cloud of gas has a total mass m and a total radius r star. We are considering a point mass inside of it at some radius little r. So we begin with Newton's second law, F equals ma. In this case, F is our gravitational energy, our gravitational force, given by minus gravitational potential, or gravitational constant, times our point mass, times the mass bound within its radius, over the little r squared. Note then that our small masses cancel out, our point mass is gone. This leaves us with acceleration equals minus g, the mass within this radius here, over r squared. Note that acceleration is the second derivative of position, and is given in terms of units by distance over time squared. In this case, we can now consider the whole sphere of gas and state that the acceleration is roughly the distance to the edge, r star, over time squared. We have a minus sign here because we're collapsing inward. So setting this equal to our gm over r gives us minus r star over t squared equals minus gm over r star squared. Note we're now considering the whole gas cloud, so we've moved to big M and big R. Our minus signs nicely cancel out here, and we can rearrange to get time by itself, giving us t squared equals r cubed over m times 1 over g. Solving this for time gives tau freefall, our freefall time, equal to r cubed over g m. And all of that is to the 1/2 power. One may note that we have something that looks like density, right? We have m over r cubed, it's flipped upside down. So if you want to go the extra mile, you can say this is proportional to rho to the minus 1/2. In the solar regime, we have a freefall time, if you plug in the radius and the mass, of about 1600 seconds, or 30 minutes. Remember this as we get to the next two, because they're vastly different. Okay, we shall now consider the Kelvin-Helmholtz timescale. This is the timescale essentially in which the star is contracting gravitationally and radiating that all out as heat. The model we're going to use is one in which we start with a shell of gas at some distance near infinity, and we look at the work done to bring it down to our distance r here. So our shell of gas, note, has a density rho, surface area 4 pi r squared, and then a thickness dr. And that's going to create our little delta m here. So we begin by looking at the change in gravitational energy as equal to the integral from infinity to r. So we're bringing it from infinity to r of the force times our little ds. And our force in this case is ma in a roundabout way, where m is our shell mass and a is our gravitational acceleration. Plugging in for that gives us gm over s squared, and plugging in for our mass gives gm over s squared times rho 4 pi r squared dr ds. Note at this point that we're only really looking to integrate over ds, so it's just a 1 over s squared here. Everything else is a constant that we don't have to worry about. So doing that gives us a minus 1 over s evaluated from infinity to r. And then we have our gm rho 4 pi r squared dr. So plugging that in gives us a minus 1 over r here. So we have minus gm over r rho 4 pi r squared dr for our delta E gravitation. The next logical step here is to look at the gravitational energy integrated. So we have our delta, now we want the full thing. To do so, we're going to integrate from 0 to a distance r, capital R. So imagine we're actually integrating like a spherical star at this point. So doing this, we have our minus gm over r, rho 4 pi r squared dr. We're concerned about little r's now. And we can note in a constant density regime, which we're considering here, we have rho equal to mass over volume. And in this case, volume, 4 over 3 pi r cubed, is going to have an r in it. So we're going to solve for m and then plug that back in. So m equals rho times v at this point. Plugging that in gives us this new integral, e grav equals 0 to r, the integral of 0 to r, times minus g over little r, rho 4 over 3 pi r cubed, rho 4 pi r squared dr. You can clean this up a lot, pull out the minus sign, and get the integral minus 0 to r, g 16 over 3 pi squared r to the fourth, rho squared dr. Note that we're looking at this r to the fourth dependence now, and integrating that gives us a 1 over 5 r to the fifth, again evaluated from 0 to big R. And so once we bring that in, we also have this 1 over 5 that goes down here, and that gives us minus 16/15 gravitational constant times rho squared pi squared r to the fifth, now big R. So at the end of the last slide, our E gravitational formula had a density in it. At this point, we're going to plug back in m over v in that density squared area, giving us E grav equal to minus 16/15 gm squared. Now here we have our density term, 9/16 pi to the minus 2, r to the minus 6, because we had an r cubed in the bottom and it was squared. And then we have our pi squared r to the fifth. So we see here that our pi's are going to cancel out, and that our r's are going to factor down, and when you do the fraction math here, you get a clean minus 3/5 m squared g over r for E grav. Note briefly that in class when we did this derivation a different way, we got a 5 over 3 here. I'm not sure if that was just something done differently or if there was like a little math error there, but it's something that maybe we can look at on Monday more. In any case, you can now claim, allegedly, that your Kelvin-Helmholtz timescale is E grav over L star. So your L is your luminosity, your E is the gravitational energy you're radiating out, and this will equal your equation here times your luminosity to the minus 1, so 4 pi r squared sigma t to the fourth, and that gives you this guy, our Kelvin-Helmholtz time of 3m squared g over 20 pi r cubed sigma t to the fourth, where once again, sigma is the Stefan-Boltzmann constant. Now you might be looking at this and wondering, well gee, what about this minus sign here? We've kind of suppressed it and waved our hands at it, but if you consider this equation, what you would really have is a minus 3/5 here, which would spit out a negative time scale, and I would consider that less than ideal. So there are ways to deal with this. One, you can suppress it, which is what we did here and in class, but two, there's a secret true Kelvin-Helmholtz timescale, which we're about to look at. So this is our very real true, better, new and improved Kelvin-Helmholtz timescale. In this case, what we've gone and done is use the Virial Theorem, which is a lengthy derivation that I will not be doing in this presentation, to get a statement that the thermal energy radiated out is minus 1/2 the gravitational energy. Note here that we have a fun minus sign that very neatly ties a bow on the minus sign we had lingering on the last slide. So in this case, our true Kelvin-Helmholtz timescale is going to be the thermal energy over the luminosity. And if we consider the solar case here, we can state that the Kelvin-Helmholtz timescale is now equal to 3 m sol squared over g, or times g, over 40, note that we have the extra 2 down here now, pi r sol cubed sigma t to the fourth, where T is the solar temperature, 5600 Kelvin. Plugging away at this gives us a timescale of about 10.6 million years. Note historically that this is why Lord Kelvin, of Kelvin-Helmholtz timescale namesake, thought the Earth could not be more than several 100 million years old because he did not think the sun could burn for much longer, and he would get into good arguments with the geologists about this. In any case, we shall now consider the Einstein nuclear timescale. This is part of what our friend Lord Kelvin was missing. It is the timescale in which we're considering the star to run if it converts its entire rest mass energy, or its entire rest mass to energy. We begin this with the classic E equals mc squared, courtesy of Einstein, and then can follow up by stating that the timescale, Einstein timescale, is equal to that energy over the luminosity. So how long it takes to radiate all of that energy out. We know then that the E is mc squared, and that luminosity is 4 pi r squared sigma t to the fourth. So we can plug in here for solar values. We have our m sol c squared over 4 pi r sol squared sigma t to the fourth, and this spits out a value of 1.66 times 10 to the 13 years. Note that this is an order of magnitude or several older than the age of the universe currently is. Also note that we believe the sun should only live another 5 billion years, so clearly something is off here. What is it? Well, two things. We're making a big approximation to begin with and stating that this E mc squared is all getting radiated out, right? In truth, the sun is not going to convert 100% of its mass to energy. It's going to convert a fraction of that, a small fraction. So we're down by several factors there. Also note that the conversion of mass to photon energy is not 100% efficient. You're losing, it's actually quite inefficient. You're losing a bunch of energy in various ways there. So that'll bring this timescale down to something more reasonable if you account for the factors we've ignored here in our approximation. With that in mind, we can now consider a comparison. So let's look at an O-type star. I picked a standard O5 here with a mass of 60 solar masses, a radius of 12 solar radii, and a temperature of 41,000 Kelvin. Note then, if you plug in all of those to our formula, you get an Einstein timescale of 2.3 times 10 to the 9 years. This is 4 orders of magnitude less than our previous solar timescale. Now it has more mass, so shouldn't it have more energy to radiate? Well, yes, that's true. However, note here that we have a t to the 4 dependence in the denominator and a significantly higher temperature in this O star. Right, 41,000 is smashing our 5,600 Kelvin sun. So we have a t to the 4 dependence, a huge temperature difference, and that means what's going on physically is that even though we have more mass to convert to energy, we are sending it out so much more as luminosity than the sun could. So we're basically just blowing it out of the water in that part. We have more energy to use, yes, but we are sending it out so much faster. Also note that the radius here is larger, so that's another factor on the denominator that causes it to radiate even more quickly. So it basically evaporates faster than the sun could. On the note of things with temperature dependences, we shall now move on to ionization. So let us first consider atomic ionization state and how it depends on temperature. This here is a plot of 3 elements I made from an old homework assignment. We have hydrogen, helium, and calcium, elements with various numbers of electrons, and we can look at their ionization temperature here. Note that in every case, for quite a while it's 0, there is no ionized element, and then you hit a certain temperature value, it spikes pretty quickly, and then you're fully ionized. So let us consider why this is the case. Well, we have 3 examples here. Hydrogen, the standard. Helium, which is a high temperature to ionize, and calcium, which seems to have a lower temperature to hit the first ionization state. So in the case of helium, what we're looking at here is that it has only free electrons. So these are valence electrons, more or less, that are hard to rip away from it, which means that you need a high temperature to do so. Hence why it's 7,000 Kelvin more than helium, or hydrogen, sorry. In the case of calcium, we're looking at an element with 20 electrons. At that point, you have a nice negative cloud beneath the outermost electrons. And so those electrons are not seeing the nucleus as positively as they could and are fairly easy to strip away. Also note that this calcium has a fraction area in about 5600 Kelvin, so considerable implications that may have for the sun. In any case, we'll now consider the hydrogen level populations. Note that the ionized level populations of hydrogen are increasing with temperature, and I generated these two plots again using the old homework, in which I've plotted the first excited state, second excited state, third excited state, and fourth excited state over the ground state plus the state in question. So what you'll notice here is that for a while, all of them hang out at 0 pretty much. But approaching 7400 Kelvin, you see that the first excited state starts to get populated quite a bit. And towards the 9000 Kelvin range, the other states start to pick up as well. Interestingly, when you look at the larger plot of this picture, you can see that past our little 9000 here, up past, say, 17,000, 18,000, the first excited state actually starts to become a waning member of this group. And instead we have the fourth excited state in red and the third excited state in green beating it. So this ties in nicely to the situation we're about to talk about, which is our Balmer lines in A-type stars. Note that A-type stars have a temperature range of 7400 to 10,000 Kelvin. So this happens to correspond quite neatly with the hydrogen partial ionization zone, which we looked at 2 slides ago. This is the same hydrogen plot, but now by itself and with this zone in gray. This is the region in which we have hydrogen that's only fractionally ionized out of the total population. So it turns out if you want Balmer lines, it's determined by what fraction of your total H atoms are in the first excited state. Recall that on the last slide we saw the other excited states start to supersede our first excited state towards the higher temperature range. Because A-type stars are in the 7400 to 10,000 band, they're nicely suited to get the Balmer lines. Also note that the highest fraction of Balmer lines occurs, we can see from this plot, at about 9900 Kelvin. Again, nicely within the range of our A-type stars. So to round that out, we can also note that we don't see Balmer lines in other stars because A, they're too cool, right? Our G-types and our K-types, our M-types are all down here in the lower temperature band and simply do not have ionized hydrogen to worry about. And our O-type stars are way up here, in which all of the hydrogen is ionized past the first excited state, so they also don't appear there. And that is why we physically see the Balmer lines in our A-type stars most often. That concludes this presentation. Thank you. I hope to see you all on Monday. Take care.